Now let's move on to paramagnetism. Paramagnetism is, as opposed to diamagnetism, where you apply a magnetic field along a direction and it develops a magnetic moment, small magnetic moment, in the opposite direction. The material itself develops a small magnetic moment opposite to the direction of the external magnetic field. In paramagnetism, it develops a magnetic moment that is small in magnitude, but that is along the direction of the magnetic field. And we will only consider the quantum theory of paramagnetism. Because there are flaws in the classical theory. The magnetic moment of an atom or ion in free space, that can be given by, if mu is the magnetic moment, that is given as gamma h cross j vector, that is equal to minus g mu b j vector. Now, there are new terms being introduced. I will have to explain what these terms are. The total angular momentum that is given as h cross j, which is nothing but the sum of h cross L and h cross s, the orbital and spin angular momentum parts. It is just the sum of these two. The constant gamma here is the ratio of the magnetic moment to the angular momentum. It is called the gyromagnetic ratio. For electronic systems, we can quantify this other constant g here, which is called the g factor or the spectroscopic splitting factor, as g mu b equals minus gamma h cross. From this definition here, this equation here, you can get this definition of g, and for electron spin, g turns out to be 2.0023, which is taken usually as 2 for electron spins, and that is what we are interested in. For a free atom, the g factor can be given by Landé equation, where g is expressed as 1 plus j times j plus 1 plus s times s plus 1 minus L times L plus 1 divided by twice j times j plus 1. This is the definition of the g factor, and we have a quantity mu b. This is the Bohr magneton, which equals E h cross over twice m c in CGS unit, and if we express it in SI unit, that is E h cross over twice m. This is the Bohr magneton, which quantifies the spin magnetic moment of one free electron. Now, we can consider the energy levels of the system in a magnetic field. The energy U would be minus mu dot B, which is mj g mu B times B, where mj is the azimuthal quantum number. And it can take values from j minus 1 up to minus j. For a single spin, and if it does not have any orbital moment, then mj, as we know, is only plus minus half, and we know that g equals 2, then u would be plus minus mu b times the magnetic field. That means, when we apply a magnetic field, the earlier degenerate states would now get splitted into energy. Now we will have two levels like this one with minus mu and this one with mu magnetic moments, with the separation in energy as twice Bohr magneton times the magnetic field. This much is the separation in energy. If a system has only two levels, then the equilibrium population ratio N1 over N, where N1 is the population of the lower level and N2 we would consider as the population of the higher level, and N is N1 plus N2. This ratio N1 over N can be expressed as e power of mu b over tau divided by e power mu b over tau plus e power minus mu b over tau. Similarly, N2 over N would be given as exponential of minus mu b over tau, and with the same denominator, plus e power minus mu b over tau. As we mentioned earlier, N1 plus N2 equals N, the total number of electrons. N1 is the population of the lower level, and this is the population of the higher level. N is the total population. With this, the projection of the magnetic moment of the upper state along the field direction is minus mu and the lower state is mu. The resultant magnetization for n atoms per unit volume, that can be expressed if we assume x equals mu b over kb t, then the resultant magnetization for the total n atoms that can be given as m equals, the difference of the population becomes useful, n1 minus n2 times mu, which is n mu e power x minus e power minus x over e power x plus e power minus x. This expression comes from these ratios that we obtained here, and this expression is the expression for tan hyperbolic x. That means the magnetic moment, the magnetization would be n mu times tan hyperbolic x. Now, if we consider low field high temperature limit, that means b is small, t is large, x would be much smaller than 1. In this limit, we have tan hyperbolic x nearly equals x. Then the magnetization would be n mu times mu b over kb t. Now, if we consider a magnetic field and an atom is in that magnetic field with angular momentum quantum number j, it will have twice j plus 1 equally spaced energy levels, and in that kind of a situation the magnetization would be given by m equals n g j mu b bj, which is a function of x. This whatever we did up to here was for two level system, and this one is for total angular momentum j, that means twice j plus 1 levels system. Here we have bjx. Now, this expression is known as the Curibrillo law. we have introduced a new function here and a new quantity x. X is given as g j mu b times the magnetic field over kbt, and bj, this quantity, this function is called the Brillouin function. Now, this Brillouin function is defined in the following way. If we have bj x, the expression for this function is twice j plus 1 over twice j cot hyperbolic twice j plus 1 x over twice j minus 1 over twice j cot hyperbolic x over twice j. This is the expression for the Brillouin function. Now, if we consider j equals half, then x, as we expressed x here, j equals half, g equals 2, that will cancel, mu b over kbt, that will be left. X equals mu b times b over kbt. This is much less than 1 for high temperature and low magnetic field. If we have this kind of a situation, then cot hyperbolic x can be expressed as 1 over x plus x over 3 minus x cubed over 45 and so on. Now, the susceptibility which is expressed as chi is nothing but the magnetization over the external magnetic field. This quantity can be expressed approximately as n j plus 1 g squared mu b squared over thrice kbt, which is n p squared mu b squared over thrice kbt. This we can also express as c over t, because only t is the variable here, c is the constant. Everything except t is absorbed in this constant c. P is the effective number of Bohr magnetons which is defined in the following way. P is given as G times J into J plus 1 squared, and C is known as the Curie constant. So, sorry, P is not this square, but power half, that is the effective number of Bohr magnetrons, and C is the Curie constant. So, this is how we describe the quantum theory of paramagnetism.